Okay, so it is a pleasure to have the second lecture from Davide Barilari. Yesterday, I forgot to say that he is from the University of Padova, and he is actually from the University of Padova. And he will speak about Sub-Riemannian curvature and 3D contact manifolds. So the stage is yours, Davide.
Thank you very much, Valentina, for the introduction. Thank you for being here also today. I tried to remove notifications, but actually there are notifications on my screen, so I don't know what to do, but I hope they will not annoy us during this time. And so today we'll discuss in the second part some results and definitions related to curvature in contact manifolds, three-dimensional, and then I will say something at the end also in general contact manifolds. And maybe I plan to say too many things, but let's see what happens. So this first slide here is just to recap what is the notation and what we already said and seen in the different talks also of Patrick. So Sub-Riemannian structure is just a triple. We have a connected smooth manifold here, as I said yesterday in this talk, just dimension is bigger or equal than 3. We have vector distribution of constant rank here, K, and a Riemannian metric on the distribution, and then on a three-dimensional manifold, which we consider most of the time, we have a contact distribution, meaning that D is the kernel of one form, where the differential of the one form is not zero when restricted to the distribution. This is equivalent to all the other definitions or conditions we have seen yesterday. And let us remember that this means also that the contact structure is Bragg generating. So one normalization which we can do is the requirement that this d omega, which is not zero on the distribution, coincides with the Euclidean volume defined by the metric. So since we have a metric, we can match the two things together. And then we can define also the red vector field, the unique vector field, such that omega over x0 is 1 and x0 is in the kernel of the omega. So we have already seen this notion also in the previous talk, but let me recall this for completeness. And this x0 is canonically associated to this Sub-Riemannian structure, is transversal to the distribution. Oh, you don't see the presentation? I've seen it.
No, I'm not seeing.
No, we see it.
We see it.
Ah, okay. So should I go on or?
I think you can go on, but maybe.
Okay. So
let me just say, sorry. If anyone has some issues with the presentation with the Teams, he can write on the technical support page.
In the presentation is shown as, I mean, at least on my screen, it's one of the participants in a way. You need to click. I need to click on the icon of the presentation and
yes,
participants.
Yes, because I am sharing from a second account as the organizer suggested me. So I don't know if it's the best one for you.
No, that's perfect, Davide. I think you can go on.
Okay, so let me just say that with this free vector field, we can build a Riemannian metric, as also Patrick said, which is somehow extending the Sub-Riemannian metric we are considering. And let me just give some intuition on a number of functional invariants we should expect on a three-dimensional contact Sub-Riemannian manifold, and try to justify with some heuristics why there will be two. Indeed, if you want to define a Sub-Riemannian structure on a three-dimensional manifold locally, because we speak, of course, of local invariants, local metric invariants, we have to assign, if you wish, two vector fields in R3, okay, just to count number of information. So these are 6 functions because of the 6 coordinates of the two vector fields, and this is an orthonormal frame for our distribution and the metric. So, but of course, if you want invariance, you should take into account invariance by diffeomorphism, so change of coordinates. Of course, when in dimension 3, so we kill 3 functions, let's say, and then also in the distribution we have a possibility of rotate our frame. So we have an SO2 invariance, and then one dimension is killed by this. So this is, of course, not a proof, but just an idea to explain why we should expect 2 functions so before looking for invariance. So, I mean, the same counting works for to say that Gaussian curvature on surface is kind of unique function invariant. Then, of course, as soon as you have 2 function invariants, you can produce more by combining them, of course. Okay, so how to get this invariance? I want to describe them first through what are called structure functions of the Lie algebra generated by the vector fields. So in my presentation, I often use vector fields, even if for some extent they are not strictly necessary, of course, to describe, because we look for intrinsic quantities, but it is good to have formulas to compute things also. So if the distribution is spanned by 2 vector fields, x1, x2, which are also orthonormal basis, and then we have the real vector field x0, then we can write down a formula for the Lie brackets of a pair of these 3 vector fields. And here we have a particular coefficients in this place. This is 0 since the properties, we can use the properties of the contact form to see that here we have to have a 0, and here you can have a coefficient 1, just because the normalization we have assigned. So the fact that d omega over the distribution is the volume form, that gives a 1 here. And then these are 0, just because you can apply the Cartan formula, okay, usual Cartan formula. And so these are functions in general on a 3-dimensional manifold, but if you consider left invariant structures on D groups, then these functions become constant, and this is useful later for some more comments. And so yesterday we spoke or introduced the Sub-Riemannian Hamiltonian big H, which is a function, smooth function on the cotangent space. It's kind of cometric, and this is a definition I recall from yesterday. And this H is a quadratic form when you restrict to a fiber of the cotangent space, and it is degenerate in general when you look to true Sub-Riemannian example. So because sometimes the Riemannian case can be included if you use some particular definition in this Sub-Riemannian one. And we have seen yesterday, we have said that Sub-Riemannian length minimizers or geodesics, depending on the terminology we use, arise as a projection of the Hamiltonian flow associated to H. Okay, no abnormal in the sense we have assigned yesterday. So this function big H contains indeed all the information. One can even start only with this big H, because indeed one can check an equivalence condition for staying in the distribution and have norm smaller than 1 to check in this way here, just using this Hamiltonian, and this symbol here is just the duality product. So so if you wish, it's an intrinsic way to check if vector is in the distribution and if it's subunit, as sometimes they are called, this vector, norm smaller or equal than 1. So let me say again that if you have a local orthonormal frame, then H takes this form independently on the orthonormal frame, where the small hi are linear on fiber function and associated to the vector fields, and we can keep, of course, also H0, the function which is associated with the real vector field. Okay, so remember that I'm using a big X0 to denote the real vector field here. So we have 2 functions on the cotangent space, on the cotangent bundle, which are canonically associated to our Sub-Riemannian structure. The big H, which is somehow the metric, and this small h0, because the real vector field is associated to the contact structure, which we normalized using the metric. So we can compute a Poisson bracket, and we will get a new function which is also invariant. And actually, if you look really to the definition of Poisson bracket and its relation with the flow of the vector field, which is associated to the Rib vector field, because I remember you that H0 is the linear function on fiber associated with X0, the Rib, then indeed this computes the obstruction for the flow of the Rib vector field to preserve the metric. Okay, so I will be more precise now. This function, when you compute, so remember that this h is a kind of quadratic and this h0 is linear. So when you compute this Poisson bracket, you get back a quadratic form again, which can be expressed with these coefficients here. But this is well defined. And what you have on this side is just a way of computing the quantity. And indeed, as you can see here, there is no H0 in the right-hand side. This means that we can treat this quadratic form on fibers actually to be defined not on the full cotangent space, but on the quotient with the annihilator of the distribution, which in the end can be identified with the distribution since we have a metric. So in the end, we can interpret this as a symmetric operator on the distribution. And so we have a well-defined trace and determinant, which are exactly associated to our invariants we want to define. And indeed, since the flow of X0 preserves the volume on our distribution, remember that we normalized the volume in such a way that d omega restricted to distribution is the volume associated to G, then one can check that the trace of this operator is always 0. So we have a first well-defined invariant, which is, if you wish, the determinant of this operator, or the positive eigenvalue. So our what we call key, here Q is a point in M, is just the positive eigenvalue of this operator, which is trace 0. And so by definition, this key is bigger or equal than 0, and it vanishes everywhere if and only if the flow of the Rib vector field is a flow of isometries for the Sub-Riemannian metric. And then I introduce a second invariant through the structure constants, or structure functions, which may appear weird, but in a while we will see more intrinsic characterization, if you wish. And indeed, I like this formula, and I will explain why in the next slide. But what one can do also is to check that this quantity is invariant by rotation of the frame on the distribution, so showing that it depends only on the Sub-Riemannian structure. Of course, this is maybe not a modern way to define an invariant, so we will see in a while what is maybe better to do. But one way is to see why this formula is interesting is the following remark, that when the first invariant is 0, key is 0, then the Sub-Riemannian structure, as I said, is invariant with respect to the flow of the Rib vector field. And then in this case, our Sub-Riemannian structure can be seen as a kind of an isoperimetric problem on a Riemannian manifold, two-dimensional Riemannian manifold, which is defined by the quotient of M with the flow. So here G is the one parametric, the group defined by the flow of the Rib vector field. So this is in general local quotient, and so in this case, this kappa coincides with the Gaussian curvature of this Riemannian surface. And it is interesting to see that the formula one can have for the Gaussian curvature of a two-dimensional Riemannian manifold with a local orthonormal frame satisfying this relation here with the Lie bracket. Okay, so if you have a Riemannian manifold, then if you know the Lie bracket of the orthonormal frame, you can characterize the Gaussian curvature through this coefficient, and because so I mean, in general, we have a formula, classical formula for Gaussian curvature with the derivative of the metric. But if you use an orthonormal frame, the metric tensor somehow is diagonalized, and all the information goes into the Lie bracket of these two vector fields. So we have this formula here, and this formula is exactly indeed kind of first part of this formula here. So you can see this relation. If this is 0, then this part here is killed, and then we stay with this. Okay, so we will see later how this invariant appear also in several geometric situations. So some asymptotic expansion of the Sub-Riemannian exponential map, or also volume of small balls, or also its kernel. So I will try to comment on all this in a while. So, but for those who would like another viewpoint on these invariants, what one can do also is to introduce kind of linear connection that is naturally associated with this Sub-Riemannian structure, contact Sub-Riemannian structure, which is sometimes called Tanaka connection, or Tanaka-Webster connection, or also Tanno connection in more general situation, or maybe also other names, because in the literature there are also other names. But in any case, it is a unique linear connection satisfying all these conditions listed here, meaning that it preserves the contact form, the Lie vector field, and the metric. And if we denote by T the torsion tensor associated with this connection nabla, then we have this relation here, number 4, saying the torsion of two horizontal vector fields is somehow along the Lie vector field, and the coefficient is given by d omega xy. And we have also this compatibility between the torsion and the almost complex structure given by J, defined in this way. Okay, so I'm not hearing anything, so please stop me if there is any problem with my can I go on?
No
so
problems.
Just... okay,
yeah,
thank
sure,
you. Sorry.
Sure, no problems. You can continue.
I have an impression of empty room.
No, we are here. We are still following. People is
good.
Here.
So we can define an operator defined here. Tau of x is just the torsion applied to x and the Lie vector field. So you plug the Lie vector field as a first element in the torsion, and you get back a symmetric endomorphism defined on the distribution. So if you give to it a horizontal vector field, it gives you back a horizontal vector field. And the property number 5 listed before can be rephrased by this Q-symmetricity property with respect to J. So you'll not be surprised if I am saying that the trace of this operator is 0 and the determinant is negative. This is just related to the operator we have discussed before, because indeed if we take the curvature associated with the connection nabla, then the kappa here appears as kind of sectional curvature along the distribution associated with this connection, and the tau, so the square root of minus determinant of tau, is just our invariant key. So this is just another way of seeing the same invariance. Okay, so this kappa can be seen here as kind of horizontal scalar curvature, if you wish, because the horizontal space is dimension 2, so this is unique sectional curvature. Okay, very good. So what is scalar curvature? What is a possible way of understanding scalar curvature. In Riemannian geometry, of course, we have a definition as a trace of some tensor, but here what we can do is I mean, also in Riemannian geometry, what one can do is to look to volume of small balls around a point. So if you take a Riemannian manifold, dimension n here, and you denote by bp epsilon, the Riemannian ball of radius epsilon centered p, and S of p, the scalar curvature at that point, then we have this well-known formula for the volume of a small ball. So asymptotic when epsilon goes to 0. The leading order term, so this one is nothing but the volume of the epsilon ball in the Euclidean Rn, which is model space. And then we have a correction term, and in the correction term, the first term is given by the scalar curvature, and it is quadratic in epsilon. Okay, so one may wonder what happens in a three-dimensional contact manifold, and indeed, just changing the notation for the ball. So we have a three-dimensional Sub-Riemannian manifold with a contact distribution, and G the metric, which is normalized. I mean, we have the compatibility between the metric and the distribution, as we have explained before. If we consider small balls, B as R, P epsilon, and as a volume, we use, if you wish, natural volume, which is just the one given by the contact structure, okay? Because we know that omega, wedge d omega, defines volume 4, and in this case it coincides with what is called pop volume in the Sub-Riemannian setting. So I'm just using this as a name for this quantity, but of course one can consider it without giving to it this name. But in more general Sub-Riemannian manifold, you can define intrinsic volume if they are equiregular, so some regularity assumption, and in this case it coincides with this. And so if you measure the volume of the ball with this volume, motion of the volume, then you can produce a formula for the volume of small balls in three-dimensional Sub-Riemannian manifold, and this is the result here. So what we can see is that, again, the leading term here is the volume of the ball of radius epsilon in the Heisenberg group. Why? Because the C0 is the volume of the unit ball in the Heisenberg group, and then since the Heisenberg group has a Lie group structure and a good homogeneity in respect to rescaling, the ball of radius r is r to the power 4 times the volume of the ball of radius 1. So this is, say, the model space. I will comment on this later. And so something disappeared on my screen now. So I'm just checking if everything is good on your side.
Yeah,
Yes.
most of us
We didn't see anything.
Okay, I'm sorry, because the screen disappeared on the laptop. But okay, I go on and you tell me if you can see what I'm pointing at. So, and the correction is order 2 here, and the coefficient is the kappa invariant. Okay. Good. This is a result I proved together with Ivan, which is here in the conference, and Antonio Lerario. So why this result is not immediate? The reason is that in the Sub-Riemannian case, as I tried to explain yesterday, the cut locus and the conjugate locus are adjacent to the initial point. So that in general, if you want to consider the set of initial parameters, which in this case are covector, which describe the unit ball, you cannot just take the full set of initial conditions, but you have to adjusted carefully because even if you take a small ball, so say of radius epsilon, there are curves which comes out from the necessary conditions, say geodesic equation, which have lost optimality in time epsilon. So that's the reason of having a cut locus which is adjacent to the initial point. And this is a picture of what is happening in Sub-Riemannian geometry. So this is the starting point here. Geodesic makes this kind of spiraling towards the direction of the Rib vector field, you have to imagine. And indeed, when this quantity is not zero, which means that the structure is not symmetric, let's say, then the conjugate locus has a cuspidal form. Creates this asteroid here, and the cut locus is this piece of surface which is in between. And Chi and Kappa describe the asymptotic behavior in the small size of this quantity. In particular, the Kappa here is involved in the length of curves which go to the cut locus and conjugate locus here, the intersection of the cut and the conjugate. So here is the point where the curve loses optimality. And we have this formula here, and for those that know by heart formulas in the Heisenberg group, this first term here is exactly the quantity you have in the Heisenberg group. So here nu is what I called yesterday PZ, so the vertical part of the covector. So remember our geodesic has two parameters, some angular parameter theta, and then a real parameter which we call PZ. So when our invariant Chi is identically zero, all this picture reduces to a vertical axis. Okay. So the analogy is like the one with the cut locus and conjugate locus on a Riemannian sphere and a Riemannian ellipsoid. So if you cut horizontally this picture, what you will see is a picture which has this form, a cusp, with a line in the middle, which is exactly the picture of a cut and conjugate locus on an ellipsoid, and which reduces to a point on the sphere. Good. Then I want to give another situation where we can see this kappa playing a role, and it is in the small time asymptotics of the heat kernel on the diagonal. Since yesterday in the session, in the question session, we had some discussion on this. I thought it was interesting to say something on this point. So in this slide, just a quick definition of how to define a Laplacian operator in the Sub-Riemannian context. What one can do is just to take a divergence of a gradient, where the gradient is this kind of Sub-Riemannian gradient. It is a horizontal vector field which satisfies the usual relation. But only for horizontal vector v, and with this formula one can write divergence of this gradient and then use Leibniz rule and arrive to this formula here for the Laplacian, which is the sum of squares plus a first order term. And in the first order term, we have the divergence of the horizontal vector field, which depends actually on the choice of the volume. So in our three-dimensional case, we have a clear volume. In general, one has to fix a volume. Independently on the volume, if our family x1 xk, or the distribution to be more intrinsic, is Bragg generating, then the operator is hypoelliptic, and we have a well-defined heat kernel. So for the heat kernel on a three-dimensional complete in contact Sub-Riemannian structure, we have the following small time asymptotics here. So in this case, again, you have a first order term here, which is given by the Heisenberg group case, let's say, and then we have a correction term, which in this case is the order of t, and the coefficient again is kappa. Okay, so here no key invariant appears, not here and nor in the expansion of the volume of small bones. So in general, to prove this kind of results, one uses the nilpotent approximation technique, which means to consider a blow up of our structure and then write down a general contact structure on the point as a perturbation of the Heisenberg one. So in the general case,
Davide, sorry to interrupt. I think I got lost for a second. What you were talking? Is this the heat kernel, or what are you doing now? What is this theorem again?
Yes, this is this P. I'm sorry, maybe.
No. Sorry, I think I just got distracted.
This is the heat kernel of the Sub-Riemannian associated with the Sub-Riemannian Laplacian. So we have an expansion on the diagonal for a small time of the heat kernel. Okay, so what I was saying is that this first main term, let's say, is what you get in the Heisenberg group, because you have a homogeneous quantity, which goes as a t to the -2, and then you have a correction here, which is characterized, the coefficient is the kappa invariant we have seen before. Okay, so actually, the existence of such an expansion is proved in much more generality, but the interesting question is I mean, one possible interesting question is to characterize geometrically the coefficients we have in the expansion in T. Okay, so please. May I ask you how much time do I have?
Like 15 minutes, more or less. But
okay.
If you want to say some more minutes, of course, it's okay.
Okay, no, it was just to see if adding something to this nilpotent approximation technique. Let me try to explain this nilpotent approximation, maybe for those who did not hear about this in an example, just a simple computation. The example of our car, okay? So we had the two vector fields yesterday defining our structure, which were this one. Okay, and then at zero, we have that x at 0 is the x, y at 0 is the theta, and their bracket is the y. Okay, so we want to do a kind of blow up at 0. It's a kind of Taylor expansion, but a little bit different, because if you consider the three variables x, y, theta, then these two will have weight 1 because they appear along the distribution, and this y, which comes as a bracket, will have a weight 2. Okay, so when you do a kind of expansion, Taylor expansion of this, here, what do you have? You have this. And here, of course, you have nothing. And then what you take the homogeneous part, the lower order homogeneous part, but with respect to this weighting here. So this guy here is something of weight -1 because it's dd theta. So you have to think that theta is the denominator if you want to give a formal meaning to this minus sign here. And this is -1, and this is -2, but this is of order 0 and this is of order 1, and the other are of higher order. So in this case, if you keep the -1 order term, you keep everything here, but in this case, you keep this plus this, and all the rest is going to get killed. And so the main order, if you wish, is dx plus theta dy, and then d theta. And here, what you have the Heisenberg group, okay? If you change the name of the variable, you will get back a version of the Heisenberg group Lie algebra, okay? So this is just to explain how this system of this technique of nilpotent approximation permits to recover, to write down, if you wish, locally contact Sub-Riemannian structure as a perturbation of the Heisenberg one. Because indeed, if you take any three-dimensional contact structure and you do this kind of blow up, then you end with the Heisenberg group. Okay. Good. Then I will go to the last part of the talk with some comments on more geometric comments on other result. So one possible instance where one can use the invariance chi and kappa is to try to classify left invariant structures on Lie groups, in three-dimensional in this case. These invariants in this case are constant and invariant in the sense that they are invariant with respect to local isometries. This is what comes for free, more or less, from what we have already said. So another interesting feature is that they are homogeneous of degree 2 with respect to dilation of the distance. So we have a property of this kind when we multiply by lambda all distances in the manifold. So indeed, if you want to classify left invariant structure with respect to local isometry and dilations, we can assume that our invariants satisfy this normalization here. So either chi equal kappa equals 0 or chi squared plus kappa squared equal 1. And of course, two normalized structures with different invariants are not locally isometric. This is the easy part. But one may wonder if two structures have the same invariants if they are isometric or not, because a priori these are functional invariants and we might miss some discrete invariants. So what one can prove is that all left invariant Sub-Riemannian structures can be classified up to local isometries and dilation as a figure that I will show in the next slide. But the main content is this one, that if you know that the two invariants are 0, then you are isometric to the Heisenberg group. If you take the other normalization, then you can see that there are no more than 3 non-isometric normalized structure, and indeed a unique one on a unimodular Lie group. So on unimodular Lie group of dimension 3, these invariants indeed gives a kind of complete classification, as we will see described by a parameter on a half of a circle. And the interesting fact is that all cases but chi equal to 0 and kappa negative, in all other cases, two structures are locally isometric if and only if their Lie algebra are isomorphic. But there is a case where we have an isometry between a group which are non-isomorphic, and I will show it. So this is the first paper where this classification appeared, but somehow with different language. So what I'm presenting here, you can find in the references I mean, the same language in the references I'm putting at the end, if you wish. So this is the picture. We have these half circles here, which is normalization. I mean, these 3 parts of circle are supposed to overlap because they are supposed to describe the chi squared plus kappa squared equal 1 with chi bigger or equal than 0. And the important part here, if you wish, are this points here, which are kind of model spaces. And so how can one read this, this picture? So if the two invariants are 0, then you are the Heisenberg group. If you fix some value of k and kappa that are not 0, essentially you are considering a line, and the intersection of this says that you have 3 different non-isometric structures with the same invariance. Okay, so here in this region you have 3, in this region here you have 2, and in this region here you have 1. Okay, and the full half of a circle is made by semi-simple, I'm sorry, yes, semi-simple group, and then the other one are solvable. Okay, very good. So if you have any question on this fact, I can go more in details maybe during the question. An interesting fact is the following result, that if you have a complete simply connected three-dimensional contact structure, Sub-Riemannian manifold, if you know, so not necessarily on a Lie group, but if you know that k is identically 0 and kappa is constant, then you are isometric, in this case globally, because you have the simply connected assumption, to a left invariant Sub-Riemannian structure, and you have the 3 cases. So kind of 0 curvature, positive curvature, and negative curvature, where you have a standard Sub-Riemannian structure on the Heisenberg group, the standard Sub-Riemannian structure on SU2, where the metric is defined by the Killing form on the distribution, and negative 1 is defined on the group SL2, actually on the universal cover. And this elliptic, yes.
Sorry, I thought you were ending the explanation of this theorem, but I see that Marcello has a question. Maybe you want to finish this slide and then, as you wish. Marcello?
Yeah, I mean, sorry, finish the explanation of the theorem. I didn't mean to interrupt in between. But yeah, my question is, are there known results if you drop one of the two hypotheses? So if you are non-complete or if you're not simply connected?
So if you are not simply connected, you can, I mean, say that you are locally isometric to, I mean, conclude a similar result, but locally and not globally. The completeness, I think the completeness also is needed to be global here. So it's just a kind of technical assumption to conclude a global result, I think, in this case, together with simply connectedness.
Yeah.
So if you wish a local result, I think you can remove them, if I'm not wrong.
Thanks.
Yeah.
Is there another question on that?
I'm not sure if it's on that, but I see that Alvaro has
to...
also the...
Yeah, thanks, Valentina. Right, so maybe my question is, I mean, if this is some sort of, I mean, it is, right, like some sort of uniformization or geometrization, would you expect, I mean, like you're sort of saying that, okay, you need to be sort of killing, right? So this psi is 0, and you also have this k, so do you have like some sort of natural candidate of a, I don't know, geometric process or geometric flow that would do this? Can I would like average the thing to kill psi and also try to make it constant curvature kappa or so?
Yes, I'm not sure I got your question. I'm
sorry. I mean, it's sort of like what would be Ricci flow? I guess is the question somehow. What would try? Yeah.
Yes, this is a good question. Actually, we could have a discussion on what should be the correct notion of Ricci in this case, actually. But I'm not able to answer in a few words here. So I can answer at the end. All
right, thanks, Davide. Let's talk later.
I mean, we have we have answers to this question. I mean, it's pretty clear what should be the Ricci flow, but it's not clear at all that it locally exists even for small time, and it's not clear that it's doing the right thing. And also, if you ask that chi is 0, so this is my totally geodesic case from my talk, right? The chi is the extrinsic curvature in my talk. So for instance, this chi equals 0. It can exist only on manifold that support a transversely Riemannian flow. So again, it can exist only on the Seifert manifold or torus bundles, and no other three manifolds.
Thanks. Yes, thanks for the comment. To complete this, if you agree, I just complete the picture. Just here you have an explicit Sub-Riemannian isometry between two non-isomorphic groups with non-isomorphic Lie algebra, because the first one is SL2, and the second one is the group of affine isometries, affine maps on the real line times R. So this is a three-dimensional group in this way, and we can describe this affine maps on the real line, of course, in this way, the coefficient A and B, with A positive, so it's positive affine maps. And if you look at this as a half of a plane, we can put polar coordinates, and you can actually write down explicitly the global Sub-Riemannian isometry between either this and the universal cover, or also this space here. So the affine maps times S1 and SL2. So this is at least in my opinion, a nice example of, which distinguishes the meaning between isometries and isomorphic in this case. Because okay, so I had a few more comments on the curvature and in invariance. So how many minutes have I left?
So I think you can take 5 minutes if you.
Okay, I will try to say something in this time. So here is kind of just notation and recap what we were saying also yesterday. So the exponential map here in the Sub-Riemannian case is defined on the cotangent space, because to identify geodesic we use covectors, and we can see this exponential map as the projection of the Hamiltonian flow. And of course, in the Riemannian case, if you like the Hamiltonian flow version, you can use that one, or you can use, say, the Lagrangian one. But in the Sub-Riemannian one, maybe it's more convenient, this Hamiltonian approach, because we do not have canonical isomorphism given by the metric, because the metric is not defined everywhere. So one possible way of studying the change of a volume on a Sub-Riemannian manifold is instead of studying how a ball shrinks to a point in the sense of studying the function R, volume of ball at center R and radius R, we can do something of this kind, which is more adapted at least to our techniques. The idea is to take an initial set of covectors, so initial set of parameters, and then to plot it along with the exponential map, and then shrink it with geodesic to the initial point. So it's like if you are plotting here a kind of cone in the cotangent space. And the point is that in this case, as I try to explain, the ball is not the image of the full cylinder. So if you want to study the volume of the ball, it's difficult to identify the set, which is plotting on the ball. But what you can do is just take a set and plot that set, maybe far from the initial point, and then shrink it with geodesics to the initial point. And then, of course, if you have a volume on the manifold, then you can induce a volume on the tangent space and take the dual volume on the cotangent space, and then you could compare this with the pullback of the volume you have on the manifold. So here you have volume mu. Here you have this reference volume, which I'm denoting m star x mu, and then you can pull back this there and try to compare the two. So you have this kind of result, which I have written only in the case of a contact manifold, which satisfies this assumption because it simplifies a bit the situation, and with the choice of the volume we have discussed before. And in this case, you can write down the expansion of this volume we have pulled back on the cotangent space with respect to the reference volume. It is interesting that in this case, in the Sub-Riemannian case, what do you have? You have a constant c. You have a t power n plus 3, which is a kind of geodesic dimension because it is not the topological dimension of the manifold, which is 2n plus 1. It is not the metric or house of dimension, but it is something that is related with the fact that we are shrinking along geodesics. And another interesting element here is this R of lambda, which is somehow a natural invariant defined along, say, the geodesic associated with that initial covector, and it is a symmetric operator on the distribution, which coincides with the say, evaluation of the Riemann tensor along the geodesic, along the tangent vector of our geodesic in the Riemannian case. So this here is just what you get in the Riemannian case. You plug twice the direction of the geodesic, and you get back an operator, which of course in this case is defined and takes value on the full tangent plane. So this is an operator which is well defined, and here we have the trace of this operator. And in contact manifolds, one can compute this quantity and see what happens in this case. Of course, that quantity is well defined, but one may want to compare it with other maybe quantities that are known in contact geometry, or Riemannian quantities, let's say. So if you use the Tano connection, which is the connection satisfying the properties I've listed before, then to describe, say, the contact structure, you can introduce two tensors, the Tano tensor Q, which is a derivative of the J map, and the map tau, which is exactly the one we have used before. And this tau will vanish when the RIB is a Killing field, and the Q is 0 if the structure is CR. And here you have somehow a formula for this quantity, showing up all these terms. And this H0 here is interesting because it is the one which contains the vertical part of the covector. So it's something which really depends on the trajectory. And the first part here depends only on the tangent vector, but of course, since geodesics are not uniquely characterized by the tangent vector, then there is this term here. So, of course, one can write a formula for this also in the three-dimensional case. What I wanted to do here to finish is to give an example of what we can do using all the machinery of the curvature, which I don't really have time to present here, but we can discuss later, maybe during the question, about, for instance, a Bohnemeyer's theorem for contact manifolds, but which is important maybe for us. Maybe it's disappointing for this discussion since we were focusing on the three-dimensional case, but also it is highlighting once more that the three-dimensional case is very special, that if you have a complete Sub-Riemannian structure, contact of dimension 2D plus 1, and we have these two assumptions here, The first one is on the Ricci, kind of a partial trace of the curvature, bigger or equal than 2D minus 2 K1. And then the second one is a bound, upper bound on the Tanno tensor. Then, if we have an inequality between the two constants, we can provide a compactness and estimate on the Sub-Riemannian diameter of the manifold. So this was not known outside the case tau equals 0 and q equals 0, but as I was saying, this particular result does not work. Our theory gives something also in dimension 3, but it is a little bit more complicated to state, because these two quantities in dimension 3, they are 0, and so the theorem should be changed, because this theorem actually need to apply when d is bigger than 1, because if d is 1, there is no, the assumption is not satisfied. So, I mean, this is just to show that there is a curvature theory. I tried to say something on this in the time I had, but I know it is not really complete, but I hope it gave you some hint or some suggestion to have a look to maybe this theory. And question, just 1 minute on question. Sorry if I'm, yes, maybe I'm late and I should stop.
I think it would be a good idea also to talk, maybe you can take 2 minutes in the open discussions and to show these open questions as if the others agree. What do the others think about it? So that
I think it's a good idea.
Maybe if, yeah, good, perfect. So let me first thank you for the beautiful talk.
Thank you
very much, Davide. Yeah, we have hearts again.
Because actually, nice. Everything disappeared from my screen, so I cannot see anything, and I cannot see what time is it. So I'm sorry if I